All right, I've been working on this for a minute, and it's not because it's hard, it's because I wrote down the wrong damn numbers, went through the entire explanation of the problem. So let me carefully, I really like this problem. So we got a mass, 0.085 kilograms, okay, and our radius, which is basically the length of that string that it's been swung around with. So I'm going to write down radius. You're going to see my stuff here in a minute. I'm writing down, and the puck makes one revolution every 0.65 seconds. So t equals 0.65 seconds. All right. And I want to talk about some of this stuff before we go too far. Okay. Now, what I need is, the main thing that I need, and we'll talk about that real quickly, is this thing is going around. All right. So here's the, say, thing that's holding the string. The puck is here. It's got a tangential velocity like this, and it's got an angular speed that's going around like this. Okay? Now, because it's going around here, and at each juncture it's got this tangential speed or linear speed, okay, which is always changing direction. Since it's on the circle, always changing direction, therefore it's got a centripetal force always towards the center. A centripetal acceleration towards the center. Okay? And notice, the only thing pulling on this thing is the tension in that string. So this is the big point. The sum of the forces on this thing, as we're going, is equal to the net force is MAC. And the only force that I see in my free body diagram is the tension. So once I calculate the centripetal force, and I know the mass of the thing, I'm done. All right? But there's some other things I want to talk to you about here. It said that it took 0.65 seconds to make one revolution. All right? That means to go around that circle took 0.65 seconds. That means t is equal to 0.65 seconds. The frequency is 1 divided by t. So in other words, if I take the frequency and I take 1 divided by 0.65, I get 1.538 hertz, which means it makes 1.53 revolutions times, it goes 1.538 times around the circle in 1 second. And in some of you that might have been schooled in physics outside the country, this, and even now, this is starting to be accepted here in the United States too, as for a proper thing for hertz, because it's seconds to the -1. Okay? So that's the frequency. And the angular speed, omega, is equal to 2 pi times the frequency. Those are all big things to know. Okay? Those are all big things to know. So, once we get, so we do 2 pi times the frequency, or it also equals 2 pi divided by the period. It's another way to write it. So if I take my 1.538 that I got for the frequency and times that by 2 and times that by pi, I get the angular speed, which is 9.6666, let's call it 9.67 radians per second. Now, I know two things. I know that V is equal to R times omega, and I've got R, which is 0.89 meters. Okay? I can do that. And then I can say, okay, I can take V squared then over R is equal to R squared omega squared over R, which is the same thing as R times omega squared. So I'm just going to do that. I'm going to take then that the angular acceleration, this is equal to the angular acceleration. And so I can take 0.89, which was my R, up at the top there, times 9.67 squared. And that's going to give me my angular acceleration. I'll just let you see what I'm doing. 0.89 times second answer. In other words, I'm taking that 9.66, squaring it. Boom. Whoa! Ha! That's about 9 G's. That thing's, well, it's going to be a pretty good tension. Times the mass of the thing, which is 0.805. And I've got 7.069. So the tension, which we discussed up here, which is the mass times the acceleration. So this actually worked better. I'm glad I had to cancel that other 10-minute video because this one was nice and concise and it showed you everything. Now to solve that problem. Is equal to 7.0. Remember, tension is in newtons. 7 newtons. Now I'm going to go to it, make sure that that works. Oh, this is only half the problem. I wonder what the other half is going to be. 7.0687. And that's newtons. Yay! That's how it happened last night. Now, the string breaks. The string breaks suddenly. Boom! Well, that ball is going to, no matter where it is, it's going to take off at that linear speed. And we know what the linear speed is. It's r times omega. What did we get for omega? 9.67? Isn't that what we had earlier? Here it is, r times omega, which I haven't put in yet because I went ahead and did it this way. But 9.67 radians per second times r's, and what was r? 0.89. So let's just put that in and call it a day. This is r times omega because that's how fast, that's the linear speed it's going to go. Times 9.67. Yeah, baby. Maybe we can squeeze one more in. Think we can? I think we can. Let's try to squeeze one more problem in. Okay. Oh, yeah, because I love this problem. Once again, 34 revolutions per minute. Here we go again. If 36.4 revolutions per minute. If we do nothing else, if we learn nothing else, we're going to learn how to convert revolutions per minute into radians per second. By gosh, that's Pearl Haggard saying in Fight Inside of Me, by golly, we're going to get this. Okay? 24 kilogram joule. I love this. What net force is acting on? What is the net force if she's standing on a merry-go-round with a radius of 1.5 meters? What's her net force? And she has it. It's her centripetal acceleration times her mass. Every freaking time. Okay? That is the net force. Now, that's because she's going at a constant speed and a constant acceleration. We can constant tangential velocity. Later on, when we get into more rotational dynamics, when we get into more rotational dynamics, we're going to be speeding up around the circle, and that changes things a little bit. We'll still have a centripetal acceleration for a split moment. We'll have two accelerations. We'll have a tangential and at a certain point, and a centripetal. But for right now, all we got to worry about is the centripetal acceleration. So let's look at the top view of this girl standing on the merry-go-round. Here she is standing on this here's the top view. Here's the top of her little head. Well, she's on the edge. Well, let's just say she's 1.5 meters. That's not a very big drawing, is it? 1.5 meters. That drawing sucks. Let's start it. But I don't want to erase this because we've done some good work up until now. So let's just draw this thing. Let's just draw this a little bit bigger. Now my circles are getting bad. It must be the late afternoon. So she's off here. Here she is, 1.5 meters away. Tangential acceleration going here, or centripetal acceleration going there. Tangential speed going this way, and omega is equal to 2 pi over the period. Okay, but in this case, they gave us omega. They said omega is equal to 36.5 revolutions per minute. Okay, so there's a couple things I want to do with this revolutions per minute. Just as bonus, I want to find the period and I want to find the frequency. Those are not asked for, but we already know that the net force acting on her is equal to MAC. And we already know that AC is equal to R times omega squared, or V squared over R. But they gave us omega, and they gave us R, so we'll just use that. Hell, we can plug in the answer right now. In fact, I'm going to do that. Because I know that the centripetal acceleration, that what's the net force acting on her, is going to be her mass, 24.5 times R, which is 1.5, times, I gotta come up with R times omega. I gotta come up with omega squared. 36.4 is not. So let's go back and let's find what omega is real quick. 30. We know we have to do this. We know we have to go. So omega is 36.5 revolutions per minute times pi over 30. That's our conversion. 36.5, because this is 2 pi revolutions, and then I've already done that once, so you can watch. So there we go. So I've got to put that in. Oh, I wonder if I can do it this way. So I'm going to get fancy with this and say, okay, it's omega squared. So we're going to take this, and we're going to take 36.5 times pi, 3.14. Do we have a pi number? No, 3.14. Ah! All right, times 3. Some of you are going, just do it the way you're supposed to. That's pi divided by 30. And then this whole thing is squared. Yeah, baby. So there's mr omega squared, where I got pi divided by 30. Yeah, there it is. What net force is acting on her if she's standing in a music that rotates at 2.8 RPMs? And she's 8.3 meters. You just did the same damn thing. Okay, so now we've got a long lever arm and a small rotation. Here we had a shorter lever arm and a faster rotation. This is revolutions per minute also. So we already know how to do it. Let's just put in the same thing. So let's just put in the force. She's still 24.5 kilograms times. Let's put in the times. Now we've got this big radius, 8.3. So this is like she's on a like a bigger ride or something. That's a nice big merry-go-round. It's a huge merry-go-round. So, and it's going at 2.8 times parentheses 2.8 times 3.14 divided by 30, close the parentheses, squared. There it is. There's my RPMs divided by pi divided by 30. So I got my radians per second. All right, boom. Oh, submit. Yeah. So then how many times a week? You all, so in part A, what was her answer in part A? 536.4. They got 536.4 newtons. So how many times her weight is the force in part A? Okay, so take 534, 536.4, 536.4, that's her force, divided by her weight, which would be mg, 24.5 times 9.8. Then close the parentheses. Is that right? What did we get? 2.234. And then you do the same thing for part D. But what I wanted to go back to real quick right here is, let's find the period and the frequency of this. If it goes around, if it's got omega, and let's figure out what omega actually is here. It's 36.5 divided by times pi divided by 30. I hit times 30. Well, getting divided by there, there we go. So it's 3.822. 3.822 radians per second. And that is equal to 2 pi over the period. So if I take this and divide by 2 pi, okay, in other words, solve for t. Well, I could have done that here, I guess, because I got 36.5 revolutions per minute. I could have just taken 36.5 to find the period. I could have just taken 36.5 revolutions divided by 60 seconds, and I'd have gotten the number of revolutions per second, 36.5 divided by 60. Boom. I got this equals 0.60833 seconds. And so then the frequency would be the inverse of that. So on my calculator, I just took, so I take the inverse of that, and I get the frequency is 1.643 hertz, or seconds to the -1. So this is seconds. I can still take it still works this way if I take omega divided by 2 pi. That will also give me my period. Let's see if we get that. So if I take that omega, which is 3.82227 according to my calculator, I'm doing the big one, divided by 2 pi. Now you got to be careful when you divide by 2. You got to go second. And I got the same thing. Because the calculator is going, you're an idiot, because this is how I did that. Okay? So that's huge.